Right. Okay. So what I thought I'd do is I'd go through last year's exam paper and we'll look at strategies of making sure we do well. And then I've looked at exemplars where the examiner has given achieve merit or excellence, and so we can learn what to do and what not to do. So this is the very first question that comes up here, and it's on the electron configuration. This is a basic achieve level question of understanding only. Now, if you have a look at these bottom ones, I'm just going to change my color to a different color. Notice how some of the students have actually, whoops, I'm going to just change this a little bit. Right, they've put down, this is just not changing the color, sorry. There. They've put down from the periodic table, they've found the number of electrons. So it's useful to have that. So you've got 19 here, because it means you can count then your number of electrons to see if it adds up to 19. So if the atomic number for potassium is 19, then you'll know I've got 1 S2, 2 S2. You can do the same if you like. Oops, that's a 6 by the way. 3 S2. Now while you're doing this you can count. So at the moment I've done 2 plus another 2 plus 6 plus 2. So I've already got 12 electrons. So I've got another 7 to go. And so that would be 3p6. So I've only got 1 more to go. And so it's the 4s1. Okay, and so a good check is then to just count, and if I use a different color now, is count up these numbers and see, do they add up to what I'm supposed to have? Yes, and you've got the CR. Now there'll always be, what I've seen, yes, one trick question, for want of a better word. So here they've got chromium, which is one of the exceptions. So the 2 exceptions, remember, are copper and chromium. And you're quite correct, so I'm not going to put that down. It's the 4s1 3d5. And then there's astatine. This one goes further on. It goes into the 4p, so it's just to check. So you'll find you'll either get a trick one like the chromium or copper, or you'll get a cation or anion. And in particular, the ones, the cations they like are transition metal cations. So if you, for instance, had chromium a 3 plus, say it was chromium 3 plus, so that didn't come out very well. But you'd have to say, okay, I had 24 electrons. If it's 3 positive, I have to take away 3, so I've actually only got 21 electrons that I must distribute. And which orbitals do they come off those 3 electrons? What's the first orbital you take out? The 4s or the 3d? In other words, am I going to have 4s1 3d2? Or am I just going to have nothing in the 4s and I'm just going to have 3d3? Okay, you'll only have the D, because remember the 4s is the outermost one, so those valence electrons get lost first, and then you start removing from the 3D if you need to. So that's for an example. Now that's achieved, and you basically, that's why they tend to give you one trick question, because for understanding at achieved level you have to get 2 of those 3 correct. That's how it's sort of been in the past, and I just assume it'll be the same way. So even if you muck up one of them, it's not a big deal. So here's an example. This from 4 students. One got from not achieved to merit to excellence overall for the whole paper. So here's an example, and you'll see this first one was a person that got not achieved, but can you see he got this one correct? Okay, so that was underlined there, and I'm not actually quite sure what they accepted over here. I think they gave it because if you mistake something, like you write a D and then you go, oh, it should have been an S, I really suggest cross something out neatly and then rather write it above it or next to it. So if you meant the 4S, write it then neatly, the 4S2, for instance. Sorry, that didn't come out that clearly. Otherwise, the examiner is going to sit and think, oh, what did you mean S or D there? So I think that one landed up getting a not achieved over there. This person got 2 of the 3 correct, so you got that one correct and that correct, but did not get that one correct because they forgot it, the exception. Again, this person also forgot the exception, but this one that got excellence, although this is only achieved one, did get all 3 of them correct. So I think the electron configurations, as they is guaranteed to come up, but they pretty much oops, okay, I've got no more, I'll go page. They pretty much achieved level. Now this is a question where you start getting what they call the insight and or in-depth and the comprehensive. So you start getting the merit and excellence over here. So as an example, what you've got to do here, whenever you have anything to do with the periodic trends in any way, radii, electron, electronegativity, ionization energy. What acronym have I used to try and help you remember what to all write? There's always something I say, remember this phrase or this thing, pens, right. So remember for pens, you have to say something about the protons. Oops, protons. You have to say something, you must probably can type better than me, the energy levels and the electrons, correct, so that's the E one. You need to say something about the nuclear charge, and the E is also for effective nuclear charge, and then the D is for distance. So you have to say something about distance, and the S is relating to the effective nuclear charge, the shielding. And you might actually have already been typing all of that, so that's great. So you have to mention all of those for what we call a comprehensive understanding. In other words, that is going to lead towards an excellence. Sorry, that didn't come out very clearly. And E7 or E8 grade. So let's have a look. I'm going to pan these up a bit so you can see. So this one student, if you have a look, did say something. So you can see the examiner said there was one correct statement. So they've said that the ion is smaller. Okay, so that is the correct thing. And they have given some supporting. It has one more shell than the K plus ion. So that gave them an achieved level. It didn't say very much further. So its valence shell is further away from its nucleus, and since the K plus ion's valence shell is one less, it has a smaller radii. They only identified one correct because they felt this was getting a little bit vague. It wasn't as clear. So let's look at an example. So they've got the right idea. This is always when I say, I can see you've got the right idea, but make it clearer, because you want to make sure that it is as clear as possible. So here's another one. They got a merit level for this particular question. And what they've said here is they've made a statement about both having the same number of protons, but they've made also an incorrect one. But because they've tied more things together, they get a merit level. So can you see that nuclear charge? So pins, so think of, you've got to talk about the nuclear charge, you've got to relate it to protons. So there is a statement there, nuclear charge, protons. Now they are talking about effective nuclear charge there. It's always good to explain how that effective nuclear charge works. So what they've done here its 19 protons are attracting one less electron. That is where the error is. So this was the error, because it's not the fact that it's 19 protons and one less electron doesn't mean that the charge, the attraction is greater. It's got nothing to do with that, that it's now focused on more electrons, so it's going to be attracted more strongly. Remember the other bits, you've got to talk about the distance. So you've got to say that, I don't think it actually, because, yeah, so it says that it has lost an entire energy level, so they've given more information there. So they've talked about distance, and so it's physically smaller. That's sort of the final tie-in. So it didn't get comprehensive. In fact, none of these examples were given an excellence level on this, because they didn't do all 5 parts of those pens. So this one had 2 ideas, but didn't give more. So if I go down, I think, oops, sorry. Nope. Oh, okay, so I only had those 2. This is now another one. So do you think you can answer that sort of question? I'll just go up again, because you're guaranteed to get something about either ionization energy or electronegativity or radii, something like that. Yeah. So you have to make sure you mention all those points. And as I say, even for this one, it looked as though they had 2 points, but they only accepted 1 because they felt it wasn't clear enough. The moment that an examiner has to start guessing, did they really mean this? Then they tend to, you weren't clear. Okay. Yeah. And actually, if you just keep on practicing this type of thing, it just follows a pattern. And so, as I said, just keep on practicing that type of question. Right, so let's go down. Here's now the next one. So it's still on trends, but they've asked it in a slightly different way. So what they've got here is you've got to now look at ionization energy. Right? It always helps to underline keywords so you can focus on what they need. So remember the ionization energy, it increases across a period and it decreases down a group. So I'm just doing it the other way around, so it's increasing upwards. So you've got to decide what is most on the right, what is most on the left, what is most on the bottom. So this one is, I hope you realize, is over there. Okay, what I'm trying to draw on that right-hand side corner is where we'd find it on the periodic table. Neon is, of course, below it. So it'll come below it. Now you are given a periodic table, so this is not particularly difficult. And boron would be sort of, well, it's actually it's about there. Okay, so ignore that, but and then nitrogen is over there. Right, yeah. So 16, 17. If that's group numbers, boron is actually group 13 and nitrogen is group 15 if you were doing group numbers. Oxygen and sulfur are group 16 and fluorine and chlorine and the halogens are group 17. But they're also all on the first period. So in terms of the highest one, which one would it be most difficult to remove an electron? So just think of where they're at, the helium. So that would be over here. Okay. Then your I thought actually this was quite a tricky question because you're going down one and you so you can debate which ones are does it increase faster or does it decrease faster. You should definitely, though, know that helium is over there. The others, if I'm thinking just... No, I've just gone for one question. The other ones I would say is... Just changing my pen color. Oops. Sorry about that. Obviously, your boron is going to be lower than your nitrogen. So you could go boron, then nitrogen, and then your neon. And you would then have to argue which ones, why you place them like this. So that would be one version. Okay. I actually thought I had given the argument over here, so I'm going to just quickly... I'm just going to quickly check down to see if I've got... No, okay. So it was just over... so they were just sort of checking, can you fill it in that way? But I thought it was a bit tricky about the neon. Is neon going to be more or less than nitrogen? Any questions on that? No. Okay. Again, that was just an achieve level question. So if you got that wrong, but you gave a good answer to this, always when it's explanation type, that's when you get your merit and excellence, and they would override. So if you got that order wrong, but you had a good explanation here, you can still get excellence. So this is an example where they said, right, we're looking at the halogens. So as I say, underline the keywords so you know what you're talking, you can focus on it. And they're looking at the polarity, and they were giving examples here, which you've now got to complete. And it's again using the periodic table. And of course, they're now looking at electronegativity. So we've had ionization energy, we've had the distance, the radius, so now it's the electronegativity. And would you have given the same? I thought this was fairly simple. Again, you look at the periodic table, electronegativity increases across, the same thing as what we had before. So fluorine sits over there, chlorine sits below it. So fluorine would be more electronegative than chlorine. So you're going to have a dipole going from the more positive chlorine to the less positive, or the more more negative fluorine. Would you have been able to put those delta negative and delta positive on? Yep. And then this example down here, we're looking at the same thing, but now we're going further down. So we've got the acetone down there, so it's further down. So your chlorine now would be the negative one, and the acetone would be the positive one. So that would be just looking at the periodic table and using just your knowledge of the trends, no explanation required. So you don't have to use pens here, because we had it earlier in that previous question. It's unlikely that they'll ask you twice to give that explanation. Here now though, is they've asked for a bit more detail. So I am contradicting myself here. So they obviously want a bit more detail, because you've got to talk about electronegativity comparing these two. So these are the ones now sitting in the middle here that you've got to talk about. Okay. And so you would use pens again here. And if I look at answers, oops, we'll go down. Okay, so here's an example. I just want to go up thinking, no, right. So here's an example where they've had to explain about bromine and chlorine. And they've got an in-depth explanation. And notice if we look at that pens, okay, they have said something about, I'm actually just going to go up a little bit to see the comment. So why this person didn't get a merit overall for this question, you can see it only got an A4, for that A4 stands for the whole question. This person understood how electronegativity was related to the nuclear charge and the distance. So can you see you've got to get more of those points together, but they didn't actually explain what electronegativity is. So you've got to show your understanding. And if they had given more points here, so if they'd gone to a higher level, they would have had a merit overall. So you might get a merit in one question, but you might not necessarily get a merit overall for that question if other parts of that question was a bit too low. So if we just have a quick look here, okay, we've got the trend. Yep. Okay, so you've got the attraction of the electrons to the nucleus. So it's done that. Okay, with underlined on the red here. So and they did talk about the bonded electrons. So they had implied their understanding, but it wasn't ultra clear. So just make sure you make it very clear. They've certainly stated that they knew the trend, but remember, just stating what the trend is, increasing along a row and decreasing down a group is not even really enough for achieved. You've got to give a bit more of a reason to it. And so they have talked about the energy levels. They call them shells, but that's fine. And so what they needed to have also spelt out perhaps is more of the distance. They haven't said as the number of energy levels increase, you're going to get a greater and greater distance between the nucleus and the bonding electrons. And they also haven't said much about shielding. So that's, if they'd just mentioned that, they would have got up this to, perhaps even if they'd got this up to a comprehensive, they could have got an E7 even for this. Okay, right, it's like a paper beneath a magnet, correct. So that's an example, and let me go down to another one. Here's an example also where they got an M6. So there was M6 overall, and why they didn't get a comprehensive for this one is, as you can see in the writing in red, it doesn't mention that the greater number of shells outweighs the increase in nuclear charge. So you need to talk about the shielding so that you can see as we getting further away from the nucleus, we've got that distance as well as in the electrons, that paper you were talking about beneath the magnet, those core electrons. So that's where they also came down in this one. I don't know if you've had a chance to read this while we were going through it. These exemplars are actually all on the NZQA site. So if you just Google NZQA 91390, they have got these exemplars there. So you can look yourself. Okay, and you'll see they have a nice detail here, but they didn't mention about those core electrons. Okay, so this is now the next question. So question 2, and so in this exam paper, remember, you've got electron configurations, you've got trends, and then another major bit is intermolecular forces. So intermolecular forces, then the other ones are polarity and shape, and then your final one is the thermochemistry. So looking at this one, they ask you to write down the attractive forces in these particular 3 given molecules. Now this is a person that got excellence, and you can see why they got sort of excellence overall, because look at the detail. They list all 3 different types. Okay, so they don't just go, they say ammonia are hydrogen bonding. They also acknowledge that ammonia has dipole-dipole force of attraction, as well as the induced dipole or temporary dipole. I've taught it as temporary dipole and permanent dipole, and those are accepted. So this one's induced dipole. This is a non-polar, fluorine is non-polar, so it only has temporary forces of attraction. And then the hydrogen chloride is a polar molecule, so it has both the temporary and the permanent. When you look at other examples of those exemplars, because this was given just an understanding only grade, if you just mentioned hydrogen bonding for ammonia, and you mentioned induced dipole or something like that for fluorine, you only need to get 2 of the major ones correct, and it would have been accepted. But to get more than that, you would have had to discuss all 3 in part B. Why doesn't HCl have hydrogen bonding? Because that's a common error, and I saw in the exemplar students said that as well, that hydrogen chloride had hydrogen bonding. I just see you typing there. Right, it's not connected to a nitrogen or an oxygen or a fluorine. It has to be small and electronegative, and nitrogen, oxygen, and fluorine do match. Students often think that chlorine is okay because chlorine and nitrogen have pretty much the same electronegativity, but chlorine is much bigger, and so it doesn't make the hydrogen as naked as it does if the hydrogen is attached to a nitrogen, oxygen, or fluorine. So just remember those 3 elements. Okay, now if you have a look at this one, it says discuss the differences between the boiling points of ammonia and hydrogen chloride in terms of the strength of the attractive forces between the particles involved. So, and then you have to describe fluorine. So you first have to compare the first 2, and then you compare with the fluorine. So try and, see what you have to do first. Mention all 3 intermolecular forces. Don't just say intermolecular forces. Intermolecular forces for ammonia is higher than that for HCl or something like that. It's too vague. That's level 2 thinking. So you need to talk about all 3. So what has the student done? The student has correctly identified that it's got hydrogen bonding. Okay. However, they didn't understand what a hydrogen bond was. And I know this is what I keep on hammering to students. You've got to be really clear what the hydrogen bond is. Because so often when I read a student's answer, it sounds as though you're talking about the hydrogen bond being the hydrogen attached to the oxygen or nitrogen or fluorine in the molecule instead of between. That's correct what you've said there. You've got to make clear it's an intermolecular force and not intra. And the easiest way is to draw a diagram. So just say in H, and if you like, just make it, you can either draw the whole thing out and then just have another NH. I've just separated an H out because then you can draw, like a dotted line between the nitrogen and the hydrogen of the second molecule, and then just simply label this as the hydrogen bond. And really that just tells the examiner straight away, you know what the hydrogen bond is, that it's the one between, and you just don't get stuck in words, because I sometimes can see the student does understand it, but it isn't clear, and the moment it isn't clear, then it's not accepted. So draw a diagram, label that intramolecular bond as a hydrogen bond, because you've got to be very particular. You've got to say that a hydrogen bond exists when you've got a hydrogen covalently bonded to a nitrogen, an ammonia, and then the actual hydrogen bond is when that hydrogen gets attracted to a nitrogen of another molecule. So you first got to give the factors that will give you the hydrogen bond in the first place, the fact that there's a hydrogen attached to an ONOF, but then you've got to say the hydrogen bond is where it's formed between the hydrogen of one molecule and the nitrogen of the other. So that's tricky, but students are often just so busy writing they don't get those two bits separated out. Okay, so I see you're typing there. Okay, so and then they have stated this a stronger bond, it's a high amount of energy, but unfortunately because they didn't clearly state it wasn't intermolecular, it sounds as though it was intramolecular. They don't get that. Okay, then this is the same sort of thing here. They've made it intramolecular, where they talk about a force in the molecule instead of between molecules. So just double check, use diagrams, and that would really help you. And again, the last bit, they got enough there for an achieved level. Okay, where they've said that HCl is a polar molecule, so it's got a permanent dipole, and so which keeps the molecules bonded. So it's saying it's a bond between the molecules. So he has stated that is, sorry. So the molecules bonded is implying the intermolecular forces, yes, between molecules. And they've said it's stronger than the temporary dipoles. Okay, so that is just a way a student sort of had the idea but couldn't put it across properly, and because of that they dropped down. Okay, if I go down to the next one, this is a very detailed person. This one got an excellence, and we're not going to go through all of this, but you can see it's C for comprehensive, which means an excellence, and that immediately ups you to an E7. If you get a good chunk at it comprehensive, you've got an E7, even if you got some other stuff wrong on the question. Okay, so they first state that it's got a higher boiling point, and do you notice they tell you all the different bonds? They say they both have the temporary dipole forces, so they aren't just going on about hydrogen bonding, they're saying they both have these, and they tell you what they are. Okay, so this is all but telling you what it is. Okay, they obviously wrote really fast, okay, and they've said they all experience this type and it's weak. And they tell you what it's affected by. So we're still on the temporary dipole force of attraction by the molar mass. So they're comparing the molar mass of HCl and NH3. And HCl is heavier than NH3, so would have stronger temporary dipole forces of attraction. And you can see that it's over there. And so they said it's got a larger mass than ammonia. And so they've compared the temporary dipole forces of attraction. Then they go on to the next bit. They've said they both have a molecular dipole. They're polar molecules. And so they carry on here. Okay, they haven't really compared much between them. And I think because you aren't given the electronegativity values, and you wouldn't know the molecular dipole for ammonia anyway, because it's the size of the molecular dipole that gives the size of or the strength of the dipole forces of attraction, and you don't really know that unless it's given. Okay, and then they go on about the hydrogen bonding. And if you look carefully at how they describe the hydrogen bonding, so it's, can you see, it's the bond between the delta plus hydrogen and the delta negative nitrogen from another molecule. So can you see they have specifically stated it, and they have stated why you've got that hydrogen bond, because of the HN bond being so polar. So can you see they've made it in two separate parts? Okay, and I think that's it for there. So this is now also in question 2, and they said, well, if I take ammonia and HCl, and now they're giving it a thermochemistry question. You will always get a thermochemistry question of some sort, and definitely a Hess's law one of some sort, which in this case you could do this one by Hess's law, or you could do this one the way they've done it here using the shorthand. If they give you all heats of formation and you have to find another heat of formation, you can use this shorthand method. If they give you combustion and other ones, sublimation or something like that, then you can't use this shortened version. So this one got everything perfectly correct, and you can see it was a merit level question because it didn't require very deep understanding, so you could only get a maximum of merit for this. And just as an example of an error that somebody did, here they went via Hess's law, which is totally valid. You could use this. Do you notice what they've done? They've written out the heat of formation, but they got the heat of they got these equations all incorrect. If you were going to do it this long way, what is the heat of formation for ammonia? How would you write it out? I see you typing. Okay, from the equation given, well, that's just the sort of the final equation. That's the one you want to end up with. So that's your final equation. But you've got to convert these three into equations. So if I try and do like the first one, the heat of formation is always forming one mole of that substance from the elements in their standard states. So ammonia is made up of nitrogen and hydrogen. So you would start off with nitrogen plus, nitrogen plus hydrogen gives me NH3, and now you have to balance. Now, can I put a 2 in front of the ammonia? Not sure? No. Okay, you're quite right, you can't. It has to be a 1 in front of the ammonia. So when you balance this, this has to be a half to get it balanced, and this has to be 1.5, or you could just make it 3/2. Okay, so that's your first one. Your next one, to make HCl, what you've got there is you've got to, so units, the elements in the standard states are hydrogen gas and chlorine gas. And of course, because you've got to have a 1 in front of the HCl, you're going to have half in front of the Cl2, and you're going to have a half in front of the H2. If you want to make NH4Cl, the heat formation, what would its equation be? So I've got NH4Cl Do you want to have a go? What elements would I have? So you can, yeah. Okay, those though are not elements. You've given me compounds and not elements. Heat of formation is always from its elements. So if I was writing a heat of formation, it has to be from its elements. So what I've got is I'm going to have, oops, sorry, 2H2, because I've got 4 hydrogens on the other side. Okay, I'm going to have half of N2, and I'm going to have half of Cl2. Okay, now what you'd have to do with Hess's law is once you've written out those equations, you'd have to sort of swap them around so that you've got ammonia on the right hand, not ammonia, ammonium chloride on the right hand side. So that one is already the way it should be. But you've got to have HCl on the left hand side. So this one has to be reversed, and you've got to have ammonia on the left hand side, so that one has to be reversed. And then you've got to just do that double check, would they cancel out? I'm not going to redraw them because I'm a little bit slow using this and my writing's quite messy. But then you would just simply, if I reverse the ammonia, what happens to the sign of my thermochemical data, my delta H? It changes sign. So if I've got to reverse that one and I have to reverse that one, but this one stays as it is, it's going to be pretty much, my final one is going to be 46 plus 92. So it never sort of picks up the first bit that I do when I put my pen down. Minus 314, and then you should get the same answer as that previous student did. So what I'm trying to say here is you can still do it in Hess's law. So this student's approach was fine. Okay, so although the examiner said incorrect approach to this calculation, it's because they couldn't write the heats of formation equations. So that way they mucked it up completely. So this was what was a pretty simple one. They just made very, very difficult. Okay, here's another example where a student did do it the simple way, but only got an achieved level. Okay, and although we say the units are for excellence, do you notice that they only got a U for understanding and not an I for in-depth, because they didn't understand that this was all per mole. So make sure you put your units down to get the best result. Now I've got a question. This answer just happens to be 3 significant figures, but did they have to give their answer to 3 significant figures? So say the answer, for instance, was 2,176. Would they have to round off that 2,176 to 2,180, for example? No, quite correct. And the reason why you don't have to round off, remember, for addition and for subtraction of measurable values, you go by the decimal point, not by the number of figures. So these are all inaccurate by in the first column. Okay, it's that 4, 2, and 6 are the ones that could possibly be wrong. Okay, because you always go, that's the level where your measurement could be perhaps doubtful. So if you had 46.0, and then 92, and then 314, you would ignore that 0 in that first one because you can't, you've got to go by the least number of decimal or places after the decimal point. Okay, that's for adding and subtracting. If I had to multiply or divide measurable values, that's when you round to the least number of significant figures. So if for some reason this was a measurable value, the 46 and the 92 was a measurable value, and I had to multiply them, they're both two significant figures, so your answer would be in two significant figures. If I had to multiply those two for some reason to get a value, then I would still give the answer to two significant figures because I'm multiplying a two significant value by a three significant value. And so that's, you always go by the lowest one. But as far as level 3 goes, it should always be 3 to 3 significant figures if you're multiplying or dividing, because they choose the values that way. But if you're adding or subtracting, then remember you don't follow that rule. So for these thermochemistry ones, when you do Hess's law, you don't round off. If you had a calorimetry question where you do multiply values, do you remember that a Q is equal to MC delta T? There you are multiplying measurable values, and that would go to 3 significant figures. Is that clear when you use 3 significant figures and when you don't? Okay, right. So basically, as far as you're concerned, Hess's law and this sort of thermodynamical data don't round off, but when you get to calorimetry, if you have a calorimetry question, you do round off. Okay, so here's one where it's now this one was the student tried the shorthand method but confused the reactants and the products, and they had the wrong sign, so they didn't even get an achieve. So they were not achieved like that other person that tried to do Hess's law and stuffed it up completely. So make sure you get your products and your reactants correct. Okay, here's now a question. You get given a graph and you've got to justify the physical changes from A to D. So this whole bit over here, you've got to explain. Okay, so you changing in time and you are increasing or decreasing in temperature. Increasing, correct. So basically you've got to justify the physical changes. So you first got to identify what the physical changes are, and then you've got to explain why it changed. And remember, by physical changes, we're talking really about gas, liquid, solid. Okay, and then you've got to also explain it in terms of the energy and the intermolecular forces of attraction. So you can't just discuss energy without the intermolecular force of attraction, because you aren't answering the question completely then. So, right, B to C, actually B to C is not melting. This bit over here is melting. Because what you've got is you've got a solid that's still a solid, and the particles are vibrating more and more and more and more until they are vibrating enough to start breaking the intermolecular forces. And here the energy is, they're vibrating more and more, and they, well, that sort of level of vibration is now kept constant because all that energy is going into breaking the bonds. So we're adding, so when we're heating, we're adding energy, and that energy is being used to break those bonds. So that's the melting bit. So B to C is what? If it's not melting, what's happening at B to C? It's changing to gas, it's boiling. Correct. So you would show you understood it by saying that the boiling point is round about, if that's 40, that would be 30. So it's round about 32 minus 34 or so degrees centigrade. So you can show you've understood that. I don't think it'll, give you extra brownie points, but it does all help show that you've understood the work. So what's really happening between A and B, you are adding an energy, and where is that energy going? Is it going towards breaking bonds, or is it going towards the kinetic energy of the particles? Okay, the kinetic energy, correct. Okay, what I'm trying to say here, there was supposed to be a K, by the way. The kinetic energy is dependent on the temperature. So as you're increasing the temperature, the kinetic energy increases. Okay, so whenever you're going up in temperature, you're going up in kinetic energy. Whenever the temperature is constant, like there, then the kinetic energy stays constant as well. So you've got to show you've explained that. So between A and B, that added energy, because remember you're heating this all the time, the temperature is going up, the added energy is going into the movement of the particles. Because they're moving more and more and more, they're starting, the intermolecular forces are starting to break. Okay, but it's going more into the vibration. Then it gets to the point where they're vibrating so much that the intermolecular forces between them are breaking. Now here we broke some of the forces. Remember, when we go from solid to liquid, we're not breaking every single attraction between them. There's still a lot of intermolecular forces there. We're just breaking some of them, so there'll be a little bit of movement around, but there are still a lot of intermolecular forces. But when we boil, you should say very clearly that you are separating the particles from each other. If you're separating the particles from each other, you've got to break all the intermolecular forces. So remember, as we're going over in time, we're still adding heat, because the Bunsen burner is still going under this beaker or whatever it is. So we're adding heat the whole time, but that energy is going towards breaking all the intermolecular forces to separate the particles. And then this last bit over here is they're all in the gas phase, and so now they're moving around, they're going faster and faster and faster, because they're still getting energy from what you're adding in, and the only way they can use that energy is using the kinetic energy, so they're moving faster. So that would be what you'd have to explain. So here's an example where they just got an understanding, so an achieved level. So they basically got that achieved level because over here they did link that BC to breaking of the intermolecular forces. So that was accepted. Yeah, and they have also said vaporizing the molecule, so they are saying it is going into a gaseous phase. But they were not clear, so they did recognize that it was in a liquid state, so they did do that, and that's why it was underlined. So it said they were not clear. They used temperature and heat energy interchangeably. They're not the same thing. A temperature is a degree Celsius. It's not energy. Energy is measured in joules. So don't use them interchangeably, because if examiners see things like that, then it immediately sort of raises the thing, do you understand this topic or not? If you start, writing those sort of things. So what they said here is to weaken the hydrogen bonds. As I say, remember, that bit is not really happening when you are still heating. I mean, some will be broken, obviously, but the main force is in building up the kinetic energy of the molecules. And that's why, you know, as you add heat, the temperature goes up. Because if you were adding heat and it was going into breaking of bonds, then the temperature wouldn't go up because it was going, the energy was being used elsewhere. So that's why this person, although they had the idea of the molecule was changing from a liquid to a gas, from A to D, there wasn't enough information given. If I go down, okay, right, you can draw on the graph as well, yes. So here's an example. They said they needed to relate the increase in temperature to the gain of kinetic energy in A to B and C to D. So they had the idea, so but were also only given an understanding grade instead of in depth. This thing over here, by the way, is for the whole question. So for the whole question, they get an A4. But for this particular one, they only get an achieved. And again, it was they could relate the energy to breaking bonds, and getting energy, but not much more than that. And I think that's it for there. So I just see we're running out of time. Here's now an example of that in-depth one. So he got comprehensive, and so got an E8. 1C would have given him E7, and you could use excited in terms of, but we tend to talk about electrons getting excited. That is a term that chemists use about electrons getting excited, but rather just talk about the molecules getting more energy. And as I say, the comment for this was that you understood that kinetic energy was related when the temperature increased, and that when the temperature stayed the same, that bonds were being broken. So what we said before, so I'm not going to go in more depth there. Right, this one, Lewis diagrams. Really important for Lewis diagrams is work out your number of valence electrons. If you don't know your valence electrons, you're going to get it wrong. So if I've got Si, what group is Si in? Same as carbon, and that's 4. Okay, fluorine is in what group? 7. So, and we've got 6 of them. So 6 times 7 is 42. Okay, plus 4 from the silicon. So we've got 46 plus those 2 over there. So we've got a total of 48 electrons that we've got to draw. Okay, and remember, if whenever we draw a line, that's the same as 2 electrons. So either 48 dots or 48 dots minus the number of lines we draw. So here's an example. So students generally did this quite well, but can you see common errors? So this person didn't put in the lines and didn't put in the square brackets. And if you get that wrong, you're missing out an opportunity. So they got a U, you can't actually see it, it's moved over, because they got that right, but this one got an I because they got both this correct and the shape correct. Now here's a common error. They got the square brackets and the charge correct, but it's so easy to leave out those lone pairs on the fluorine or chlorine or something like that. So make sure you count your number of electrons, 48, and you distribute them. Count, make sure that they're there. Okay, this is now entropy, because this is going to come along. So here we're basically saying we've got an endothermic reaction. It's a cold pack, so it's getting cold, but it's a spontaneous reaction. And you're going to get something like this in some way. So it's either going to be dissolving something or an ice pack, something like this. So here is something it's dissolving. So you can see it's a solid, whoops, it's a solid going to aqueous, so we know it's dissolving. And you've got to explain the entropy correct. That's a really important point. You've got to say that for a spontaneous reaction to happen, the overall entropy must increase. You could talk about Gibbs energy, but that's not at level 3, but you do know a bit more, so you could talk about that. But they would be looking that you'd say the overall entropy has to increase, and then you'd have to talk about the surroundings and the system. So the system is the reaction, and the surroundings is obviously the air or whatever surrounding that reaction. So in this particular case, they've correctly said that the entropy increases, and they've understood what entropy is, so they get a merit level. They've seen it as in depth. Okay, this one also gets it in depth. There wasn't really an example of a comprehensive, although I don't think this actually went to comprehensive level. So it says it has clearly understood what entropy is and linked it to the question. So as I say, as long as you've got those 2 points of the system and the surroundings. Yep, correct. Okay, so here's one where you're now told to explain what happens for the system and surroundings. So it's actually helping you give more detail. And so here's an example where the explanation was wrong, but they had the ticks correct. So they get an understanding level. So you get at least an achieve for this part of the question. But what they've got wrong here is they got, where was it? Okay, they've got something in an endothermic reaction. More energy is used to break up the bonds than to form them. So that was correct, but it wasn't directly related to the entropy. So what was happening to the entropy of the system? How it was related to the heat. So you've got to say, as you add, if they're taking heat out of the system, you've got to say that the particles of the if you're taking, because the system's getting colder, it's sucking in energy from the surroundings, which means the kinetic energy of the surrounding particles decreases, so it becomes more ordered. So there's going to be more entropy in the surroundings. So you've got it, because there's I have confused myself a lot there, and I see it's actually time, and I think I've used my 1 hour of brain's worth. Yes, I just went blank there. We can leave it in there. So that one's here clearly understands it, and you can leave it at that. Sorry, sometimes I start and then I get myself confused still. Yes. Okay, right, so we'll stop there. Was this beneficial? Would it help? Because I thought of next week doing the same thing for organic. Was this helpful at all? Yep. Okay. So because I say your practice exams in 2 weeks, so at least we've gone over this one. We didn't quite finish, but as I say, you can find all of this on NZQA. They've got those exemplars there. And then we'll do organic next week, and then we'll carry on and finish the aqueous systems in September. Right. You have a good rest of the week. Right. Bye.